Hello Vulkan developers! We all know that great graphics require high quality, high resolution textures. But in real-time rendering, those textures are viewed from varying distances, whether up close or far away. To prevent severe aliasing and performance drops, we need a Mipmap chain so the GPU can sample the best texture resolution. In OpenGL, this is a breeze. Just call GL generate texture Mipmap after loading your texture and let the driver handle the rest. But Vulkan, being Vulkan, doesn't give us a magic one-liner. We have to do the heavy lifting ourselves. Today we are building a robust Mipmap generator you can use for both online rendering and offline tools. Let's get into it. Before we get started, I'd like to say a big thank you to Simon, who recently joined 3D Underground. If you too would like to support this channel, you can do that at patreon.com/ogldev or by joining the YouTube channel as a member. The implementation of Mipmap generation requires changing the code in a number of places. In each section, I'll work my way from the bottom up. This way, you'll see the relevant changes in the Vulkan API, as well as how I integrated it into the system. Hopefully, you will be able to adapt it to your own code base. Let's start in the createImage function, which is a low-level private function in the Vulkan core class. This function creates the image handle, calculates the image memory requirements, allocates that memory, and binds it to the image. We have a one-line change in this function, which is to specify the number of Mipmaps in the vkImage createInfo structure. Previously, it was hard-coded 1. Now it's a new parameter of this function, which we need to set into the structure. This allows Vulkan to allocate a larger memory buffer when multiple Mipmaps are requested. This also means that there is a strict assumption in the Vulkan specification about the size of each Mipmap, which is 1/2 of the previous level, rounded down, with a minimum of 1. The function createImage is called from 3 different locations. First, it is used to create a depth buffer. Here we don't need any mipmapping, so the mip count is always 1. There is also a public function called createTexture, which can be called by the user to create a texture without initializing its contents. This function is used in the Compute Shader demo, and for now it also uses a hard-coded mip count of 1, which leaves us with createImageFromData, which is used to load textures from files, for example, when a model is loaded by the SIMP library. This function gets the mip count from a utility function called calc_num_miplevels, which takes the image format and dimensions as parameters. The calculation requires getting the maximum between the width and height, calculating the base 2 log of the result, rounding down using the floor function, and adding 1 for the original image. Notice that this code is executed only if the format feature sampled image filter linear bit is set in the optimal tiling features attribute in the format properties. Otherwise, the mip count is 1. This check is necessary because we are preparing to use BlitImage to generate the Mipmaps, and Vulkan strictly mandates that the image format must support hardware-accelerated linear filtering to do so. Some platforms lack this support and will need a different way to generate the Mipmaps. We get the properties of the specific format using a helper function in the physical device class, which calls getPhysicalDeviceFormatProperties on the requested format. The mip count is passed along to createImage, and we all know what happens to it down there. Next up is updateTextureImage, which actually loads the image data into the Vulkan image. This is where we will create the Mipmaps. The way this function used to work is that it would create a staging buffer, populate it with the image pixels, and then copy it to the image on the GPU. For this copy to work, we have to transition the image layout from undefined to transfer destination optimal, perform the copy, and then transition from transfer destination optimal to shader read-only optimal. The transition function is simply a wrapper for beginning the command buffer, placing a barrier in it, ending the command buffer, and submitting it into the queue. The main change in this function is what happens after the copy operation. If the MIP count is 1, the original behavior of transitioning from transfer destination optimal to shader read-only optimal is maintained. Otherwise, the image remains in transfer destination optimal, and the new private function, generate Mipmaps, is called. This function takes the image handle, dimensions, format, number of layers, and the number of Mipmaps. We start by beginning the command buffer. This command buffer is a private attribute of the class called copyCmdBuff, which we are reusing during the initialization for all sorts of tasks. There's no problem with that because we submit it into the queue, wait for it to complete, and only then reuse it. The core part of this function is this loop here over the number of Mipmaps. To downscale each Mipmap level to the next, we use the Vulkan API cmdBlitImage. This is a very powerful command which provides several capabilities. It can scale and downsample images, it can perform format conversions, it can crop or flip the image, and more. The main challenge here is handling layout transitions correctly. Vulkan allows you to have Mipmap levels in different layouts, and this is critical because the blit operation takes place internally in the image. After the copy operation from the staging buffer in the previous function, the entire image is in transfer destination optimal. To perform the blit, we need to change the previous level to transfer source optimal, and the target level needs to be in transfer destination optimal. After the blit, we are done with the previous level, so we can transition it to shader read-only optimal to be used for sampling during runtime. The loop begins in the second level, level number 1, because level 0 contains the original image and doesn't need to change. We execute an image barrier on the previous level and transition it from transfer destination optimal to transfer source optimal, as I've mentioned. The last two parameters to the image memBarrier function are the number of levels to process and the level index. Next, we calculate the dimensions of the current level, which is the destination of the blit. Next, we set up the image blit structure, which is where the blit is taking most of the parameters from. The source is the previous level. The source offsets are 0, 0, 0, up to the dimensions of the previous level. The destination resource is the current level, and the destination offsets is what we've just calculated. We can now execute the blit operation. This function takes the command buffer handle, the source image and its layout, the destination image and its layout. In this case, the source and destination are the same, but obviously you can also blit between different images. Next, we have the address of an array of image blit structures and its size. Finally, we specify the filter type. For best results, use linear, but you can also use nearest. After the blit, we transition the previous level from transfer source to shader read-only optimal. For the next iteration, we also need to copy the current destination dimensions to the source dimensions. The new destination dimensions will be recalculated at the start of the next iteration. After the loop is complete, there is still one more layout transition that we need to do on the very last Mipmap, the smallest one. The transition to shader read-only optimal always happens on the previous level, but we are missing the last level, so we need to do it explicitly here. Finally, we need to submit the copy command buffer. This means ending it, submitting it into the queue, and waiting for the queue to finish. This is not the most performant way to do it, but we are still doing things in the simplest and safest way. We will need to optimize it in the future. So this is the main action, but there are still a few more bits and pieces that we need to take care of. First, we have the creation of the image view. The image view create info structure contains a sub-resource range, which contains the MIP count. Previously, it was hard-coded 1. I've added the MIP levels parameter to the wrapper, which we need to set here instead. The wrapper is called from several locations in the code. The creation of the swap chain, the creation of the depth buffer, and the creation of the texture without an initial content. In all these places, we pass 1 as the MIP count, so there is no change. The only place where it matters is create texture from data. The function createImage from data returns the MIP count, and we pass it on to create image view. We also need to update the creation of the texture sampler. Instead of max LOD of 0, we use the special constant vkLOD clamp none. This means that the system doesn't clamp the calculated LOD during runtime. The most important change is in image mem barrier. This function now takes the number of MIP levels affected by the barrier and the base MIP level. Instead of base level 0 and the MIP count of 1, we use the provided parameters. In addition, I've added a couple of cases that the function handles. The way this function works is that we provide the old and new layouts, and it determines the access mask and the stages. So when we transition from transfer destination optimal to transfer source, the source access mask is transfer write and the destination is transfer read. The stage is transfer for both source and destination. Going from transfer source optimal to shader read only optimal means that the source mask is transfer read and the destination is shader read. The source stage is transfer, and the destination stage is the fragment shader. If everything is working correctly, you should notice some change in the appearance of textured objects, depending on the distance. Hopefully, it looks better now. You can also use RenderDoc and verify that the MIP chain was created correctly. Now, I don't recommend using this code in an actual game because it might increase the load time. This is okay for testing and small samples, but for a real product you probably want to save the Mipmaps to some file and then load them during runtime. And that's it for today. Thank you for watching and I will see you next time.